Yeah. 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 So we have reduced to the case when v is v is v lambda 1 and lambda is lambda 1. Yeah. And if v minus lambda is 0 on v, then of course v is every element of v, every non-zero element of v is eigenvector. Yeah, so that is the simplest case. But more generally, what will happen is we will take w to be phi minus lambda iv, and w need not be 0. Yeah, so if w happen to be 0, then we already have the Jordan form. Yeah, this. At one step we get, I mean, diagonal matrix is a Jordan form, right? So in general, we'll get W is some subspace of V. In fact, since lambda is an eigenvalue, we know that the kernel of phi minus lambda I is non-zero. Yeah. So W is in fact, can you still hear me?
Yes, sir. Now.
Yeah. So it said something is wrong. So that's why I checked. Okay. So we get that W is in fact a proper subspace of V, because it has a kernel, so the dimension of W can't be whole of V. Yeah, it's not a bijection. So dimension of W is strictly less than the dimension of V. Okay. So now we will use again induction on the dimension of V. Yeah. So first of all, again, W is phi invariant subspace. Yeah, because W is phi minus lambda IV. So if I apply phi, then again I can move phi the other side. Yeah, and like we did earlier. So W is again a phi invariant subspace. Phi of any element of W is again in W. Yeah. So so W is a phi invariant subspace, and even N is also phi invariant, right? Because why is N phi invariant? But maybe yeah. So if so you can check if N is also phi invariant. Yeah. So if you take some vector v such that phi minus lambda I v is 0, then phi v will also have that property. Okay. So in fact, phi v is just lambda v, and then again, if you apply phi, then you'll get lambda square v, and so it will phi v will be annihilated by phi minus lambda I v. Phi minus lambda I. Okay, so they both N and W are phi invariant. Okay, but maybe N being phi invariant is not important for us. W is phi invariant is important for us. Yeah. So it so happens that N is also phi invariant, but more importantly, W is phi invariant. So hence, by induction on the dimension, there exists a basis. So what is happening is, see, if everything was eigenvector, then at one go we get it. Yeah. But if it is not an eigenvector, you have a generalized eigenvector of index 2, exponent 2, let's say. And if I apply phi to it, then it becomes an eigenvector. Yeah. So so the matrix will somehow change a little. So we should have. So for W, we can apply the induction hypothesis, and we'll get some diagonal matrix, and combining it with this, so you'll see how it works out. Yeah. So by induction on dimension, there exists a basis B of W such that phi restricted to W has a Jordan form. Yeah. Has a Jordan form. Yeah. So has a Jordan form means phi restricted to W has this kind of Jordan form. So in other words, if we want to write it in terms of vector spaces, decomposition of vector spaces, that is same as saying we can write W as W1 plus W2 up to WL, where WI's have dimension, some fixed dimension Ni, and WI's are phi invariant subspaces. So that I haven't written. Ni, Wi, phi invariant, and Wi contains a generalized lambda eigenvector Ei of exponent Ni. Yeah. Yeah. So see, W has this basis. Yeah. So sorry. So maybe I need to justify this a little bit. So so phi restricted to W has a Jordan form, means with respect to basis B means so where should I explain this? Yeah, maybe I'll do this. Yeah. Yeah, in this gap I can explain. Okay, so this is because so phi restricted to W has Jordan form. Let's say there is only one lambda. Yeah, so the J lambda n1 to J lambda NL. Yeah. Yeah. With respect to B. Yeah. So you look at first n1 vectors of B. Yeah. So let's say V. So let's call it E1. Yeah. So or rather, let's look at the first vector of B. Yeah. So let's call it E1. And remember, J lambda is n1 is basically, it looks like lambda 1 and so on. Yeah, this is how it looks like, right? So what does it tell us? That phi of E1 is lambda E1 plus E2. Yeah, this is what it tells us, right? So that in particular it tells us that E2 is phi minus lambda I of E1. Yeah. And so on. E3 is phi minus lambda I of E2 and so on. Yeah. Up to En minus so here we'll have to go to I mean in the previous one we started with V0, and that's why we went till Vn minus 1. So here I'm starting with E1, so I have to go all the way to En. En is P minus lambda I times En minus 1. Okay. So using this identity, phi E1 is lambda E1 plus E2, phi E2 is lambda E2 plus E3, and so on. We get that, yeah. So eventually you get that En is phi lambda phi and using those identities we get these things. Yeah. So what we are getting is that the first n terms of the elements in B is precisely given by the basis constructed from E1 in the previous proposition. Yeah. So we can partition B as E1 P minus lambda E1 phi minus lambda I square E1 and so on. Phi minus lambda I for n minus 1, n1 minus 1. So one has to go till n1. Yeah, n1. n1 minus 1, e1. Okay, so this is the first n1 elements of the basis, and then you'll have e2 and so on. So you'll get some term up to n2 elements, and then you'll have to go el, and then again phi minus lambda I, el, and so on till the last element. Yeah. So I'll not write the last element, but you know what it is. Yeah. Phi minus lambda I for nl minus 1 el. Yeah. So this is your basis essentially, right? So if you take so this is my definition of E1. So W1 is basically generated by the first N1 elements. W2 is generated by the second N2 elements. W3 is generated by the third N3 elements, and so on. And WL is generated by the last NL elements. Okay, and EIs are as defined. Yeah. So this I statement is what I have explained you right now. How you get this decomposition of W using the Jordan form. Yeah. So this translation we always should do. Yeah. So the concrete statement about the matrices we should translate it in terms of vector spaces and subspaces and back. Getting this decomposition is equivalent to giving this this matrix. Yeah. Is this clear now? Why you have this decomposition of W?
Yes.
Yeah. Nivedita?
Yes.
Yeah. Anargo, anyone has a question? No? Okay. So we got this decomposition of W, and this is assuming, so we were using induction on the dimension of W. So this has a Jordan form, so we got this decomposition. Yeah. So once we have this decomposition, now what do we do? So now we'll have to, but this is not enough. We'll have to get a decomposition of V. Yeah. So V is not, I mean, W is just a subspace under this image. So now we'll have to somehow lift these EIs to, so remember, if we, so EI is the image of phi minus lambda I. EI is the image of some element of V under phi minus lambda I. Yeah. So let's look at the pre-image of yeah. So let Vi in V be such that so maybe let me just put a gap here so that it's more readable. Yeah. Yeah. So now you take so maybe I'll just write one more line so that it becomes slightly clear. Yeah, so I said this, but maybe Wi is just span of EI phi minus lambda I lambda I EI up to phi minus lambda I for Ni minus 1 EI. Yeah, so you take Wi's to be this, and that is the decomposition we are talking about. And we already saw that these are phi invariant. Yeah. Okay, so now what we do is we pick a Vi in V such that phi minus lambda I Vi is EI. Yeah. So say EI. So we have assumed that EI has exponent Ni. Yeah. Then what will be the exponent of Vi? It will be Ni plus 1. You'll have to do kill it by one more guy. Yeah. Then only it will get. You'll have to operate phi minus lambda I one more time. Then only it gets killed. Okay, so then Vi has exponent Ni plus 1. Yeah. for I between 1 and L. Right. So now what you do is you take Vi to be the subspace generated by these guys. So Vi, then phi minus lambda I, Vi, then Ei, and all its subsidiaries. Yeah. And so on. Yeah. Is that okay? So V minus lambda I power j Vi, j greater equals 0. So I mean, and then maybe less equal Ni plus 1. Yeah. So you'll get Vi is a vector space of dimension Ni plus 1, if you like, right? Wi was a vector space of dimension Ni. Vi is a vector space of dimension Ni plus 1, one more. Yeah. So we get these vector spaces. And what is the image of Vi under phi minus lambda I? It's precisely Wi, right? Because Ei goes to Vi goes to Ei, and Ei will go to phi minus lambda I of Ei, which is already in Wi. Yeah. So image of Vi under this phi minus lambda I is precisely Wi. Yeah. So now we look at this subspace U equals. So now so what we'll show is that V is direct sum of these Wi plus something more. Yeah. See, when we apply this phi minus lambda I to V, where is this? Then what will happen? So all the eigenvectors will get killed. Yeah. So everything which is in N will go to 0. So we'll have to capture those eigenvectors as well, but we'll also want to capture the pre-image of W. Yeah. So what happens is V is going to be N plus something. Yeah. N plus something whose or rather, let's say not necessarily direct sum, N plus something whose image is W, whose image under phi minus lambda I is W. Yeah. So I'm trying to capture that something as U. Okay. So that is what I'm trying to do. So this U, I'm taking it to be the sum of these. So VIs are subspaces of V, and I'm taking U to be the sum of these V1 to VL. Okay. So first thing I want to say is that U is actually a direct sum of V1 to VL. Yeah. So this is not just some ordinary sum. So there is no intersections. Yeah. So every element of U, you can write it uniquely as sums of elements of V1 to VL. Okay. So a priori, if I do the sum, it need not be a direct sum, right? So first claim is that it is indeed a direct sum. So V1 intersection direct sum of V2s, sum of V2s is 0. Yeah. Okay. So I'll prove the claim in a bit. Yeah, we'll prove the claim in a bit. But assuming the claim, let's complete the proof, and then we'll come to the proof of the claim. So suppose we have proved U is direct sum of V1 to VL. We already know that VIs are phi invariant subspaces, but U need not be whole of V. Yeah, U is still a subspace of V. So this is contained in. So maybe one should think of it as a subspace of V. Yeah. So and what happens when we apply phi minus lambda I to U? So if we apply it to Vi, it goes into Wi. Yeah. So if I apply it to whole of U, it will contain. It will be contained in. It will be equal to direct sum of Wi's. Yeah. There I can say direct sum because I mean Wi's. So we know that W is an internal direct sum of Wi's. Yeah? So we get that phi minus lambda I of U is whole of W. Okay. So since phi minus lambda I of U is whole of W, what we get is V is U plus N. N was the kernel of phi minus lambda I. Right? Why is that? Why is V U plus N? So the point is, if you take So let's take V in V, yeah. So we want to show that it can be, I mean, I'm not saying direct sum, I'm just saying sum, yeah. So I want to say any vector in V, you can write it as a vector in U plus a vector in N, not necessarily unique. So if I take V in V, what is the U we can, how do I choose U? So what you do is look at phi minus lambda IV, yeah. This is going to be in W, right? Because W is precisely the image of phi minus lambda IV, yeah. But so this belongs to W, but image of phi minus lambda U is also W, yeah. So what we can do is we can also find an element in U such that its image is same as this thing, yeah. So there exists U in U such that phi minus lambda I U is same as phi minus lambda I V, right? Is that okay? And now if you look at the difference, U minus V or V minus U, yeah, that of course belongs to the kernel because their images are same, yeah. So this statement tells us that V is of course V minus U plus or rather U plus V minus U. Let me write it this so that it's consistent with U plus V minus U. Yeah. You will cancel out, and but this is in U, and this by choice is in N. Yeah. So every element in V can be written as something in U plus something in N. Okay. Or you can think of as third isomorphism theorem if you like. Have you seen, by the way, isomorphism theorem for vector spaces? First isomorphism theorem, second isomorphism theorem. Has anyone seen maybe? Oh, so no one has seen? Okay, so maybe after the Jordan form, we'll discuss something about the isomorphism theorem. So that's, yeah, so maybe, yeah, that's one more aspect one can do. Okay, so let's try to complete the proof. So V is U plus N, yeah. So, but this need not be a direct sum. But what we can do is you can, I mean, if you squeeze N, yeah, you can find a smaller subspace of N such that V is direct sum of U plus N prime. Yeah, wherein basically what you do is take a basis of U, yeah, and then you extend it to a basis of V with elements in N. That you can do because V is U plus N, right? So you can, and then the remaining vectors which are in N, which generate will generate a subspace of N. That subspace you call it N prime. Okay, so there exists N prime. So this implies, so maybe this we have done. So maybe I should say so. So here is the explanation for this. So there exists N prime in N such that V is U plus N prime. And hence by the claim, we have V is V1 plus V2 plus VL plus N prime. Yeah. So now you consider the basis VI to be, so basis of VI, you know what you have to take. VI plus phi minus lambda I VI plus phi minus lambda I square VI and so on. That has to go up to